In this video, I want to take a look at how I could actually determine whether a vector field is actually conservative or not. And we've talked previously about how we could do this. We could attempt to find a potential function for our vector field f. That is, we could find some function whose gradient is going to turn into what we see as the formula for that vector field. However, that can sometimes be a little bit difficult to do. And just because it's difficult to do, and we haven't found a way to do it yet, doesn't mean that it's not possible. So with all the ideas that we talked about in the previous video, we can start to try to put together some strategies for how we could answer a question like this. So I'm going to show you how I can use some of the strategies specifically here that I have from some of the previous theorems that we have talked about in the last video. So here's what I have. Here I'm going to start on example 6 by just quickly noting the domain of my function here. So I'll say, since f is defined on, well, let's see, there doesn't seem to be any restrictions on what x or y could be here. Nothing I can plug in for x or y is going to make anything here undefined. So I guess this would be defined on all of R2. And I can see that the components of f of x, y will have continuous first order partials. But what that means is automatically then the two most recent theorems may apply here. I have continuous first order partials and I'm defined on R2. One thing that I might notice about R2 is that if I quickly think about all of the space of R2, which is going to be, well, everything here, I can definitely see that this last theorem seems like it might apply, because I could ask, is R2 open? Well, remember that the definition of open was no matter what point you select in R2, can you draw a circle around it so that way only points in the only points in the circle are going to be also a part of R2. Well, that seems guaranteed. So I know that R2 is going to be open. But I also can tell that R2 is simply connected, because any points that I pick in here that simply connected, meaning that any point that I pick in here, if I draw a curve that doesn't intersect itself and starts and stops at the same point, only covers spots in R2. So I'll note right here, R2 is open and simply connected. So this is how I know that I kind of have the last two theorems both applying. It seems like the conditions are met. But here's one thing that I could take a look at. If I'm looking at this last theorem, I would need to see if I take the partial derivative with respect to y of my first component and partial derivative with respect to x of my second component, if they're equal, then I can make a conclusion. So let's see what we have. We see that the partial derivative of p with respect to y, again, p is right here and q is right here. With respect to y, I get -1. And my partial of q with respect to x is going to be +1. But then I can see something. Clearly, it turned out to be the case that these two partials did not equal each other. And so I can think here for a moment, well, wait a minute. If these two things didn't equal each other, what does my most recent theorem tell me? This said if they did equal each other, then you would be conservative, but it doesn't say anything about the reverse. Let's look back at the previous theorem. This says if you